All right, today I'm going to show you guys a couple of cheat codes when it comes to the ideal gas law. So the cheat codes, and the reason I show students the cheat codes is because a lot of times professors just kind of expect you to be able to make some general changes to some of the measurements in the ideal gas law. And those professors are kind of silly when they think that's going to happen for most students. So the idea today is I'm going to give you two variations of the ideal gas law. So basically, when we use the ideal gas law, we have three equations. You have the original, and then you're going to have these two. And you're going to use these two when you see some things that are given to you that you're not quite sure what to do with them. So real quick review. So N is moles. Now, back in the day when we learned how to calculate moles, and we used choo-choo tracks to do this, the idea is if you were given a mass and you wanted to convert to moles, you would literally just take the mass of the sample divided by the molar mass. Okay, that's what moles is. So like if I had 15 grams of oxygen and I wanted to figure out how many moles that was, I would divide 15 by 16 because that's the molar mass of O, and that would give me my number of moles. Well, a variation to the ideal gas law that we can use is one that uses mass and molar mass. Okay, I'm going to show you where all this builds up, and you guys are going to want the final equation here. But the idea is this: if instead of PV equals nRT, I substitute a little m over a big M. Now, big M stands for molar mass, and I'll give you guys what those things have to be measured in today. So, equation of the day, one of the two equations of the day, is not PV equals nRT, it's PV equals little m RT all over big M. Usually molar mass is a cursive M. I didn't take the time to select that on the font there. That's our equation, okay? So how does it differ? When do we use it? We literally want to use this equation, and you can use this equation if you're given or solving for mass. So for example, if a problem gave you, you have 12 grams of NH3 gas. Well, that 12 grams is what you'd put here, and the molar mass of the gas in this case would be NH3, which is 1 nitrogen, 3 hydrogen, 17 grams per mole you'd put there, okay? Keys with using this version of the ideal gas law. Mass needs to be in grams. Molar mass for us is always in grams per mole. That allows everything else to cancel out, okay? So pressure still has to be in ATM or kPa. Volume still has to be in liters. R is going to be whichever one you want to use based on your pressure. Temperature needs to be in kelvins. And those are going to be the measurements you need for that one. So that's number one. We'll do a couple of examples with this example here, okay? If mass is given to you in kilograms, that ain't going to work. You have to convert to grams before you plug it into your equation. So one of those little things that professors get you on, okay? So that's one. You can also take this equation and rearrange it for density. So like I said, you don't have to write this down. We'll get the final equation here, but I'm going to show you where this comes from. So back in Miss McCarville's day, she said that density is equal to mass over volume. Okay, shot through the heart. So density is equal to mass over volume. Well, when you look at this equation here, I see mass and I see volume. So I can take this and I can rearrange it to get mass over volume and then get the rest of the stuff on the other side. This version of the equation is what you're going to want to use when you are ever solving for density or calculating density. So density is equal to pressure times molar mass all over RT. Pressure times molar mass over RT. That's going to be what we use. Now, here's the key. The density has to be in grams per liter. Everything else has to be molar mass, grams per mole, ATM or kPa, use the correct R, temperature needs to be in Kelvin. So the reason I'm giving you guys these is because it's going to make your life a little bit easier in deciding, calculating gas laws and stuff. So you don't have to do the algebra to kind of solve for and find the equation within the equation. So 3 equations that you have: the original ideal gas law, the one that has mass and molar mass, and the one with density. Okay. Now, when will I use the one with density? When I'm asked for density or I'm looking for density. Okay. Or when density is given to me. That's when I would use that. Okay. So we're looking at an example problem here. Typically, to use these two, you have to know what the gas is. Because if you don't know what the gas is, then there's no way to figure out the molar mass is. Right? So I'm going to find the mass of O2 gas at 1.55 ATM, 250 milliliters, and 25 degrees Celsius. So we got to do some work here. Okay. So pressure is 1.55 ATMs. Volume, can't deal with that. We've got to use this value for liters. Temperature, can't use that. We'd have to add 273 to that. So that's 298 Kelvin. Where I got that, I just added 273 there. Okay. Mass is what we're solving for. So we don't know what that is. If we are looking for mass or we're given mass, then we got to somewhere have the molar mass. And this is the most important key to that. You got to be given the molar mass, or you got to be given the formula for the compound in order to figure out what its molar mass is. So we grab our periodic table and we'd say, all right, O2 is 2/16, so that is 32 grams per mole. Okay, 32 grams per mole. Typically, I will tell you with sig figs, I'm not going to be too specific on sig figs here. When we look up molar masses, we typically never use those for sig figs. If you want to, that's fine. If you want to keep 3, that's fine. Obviously, you could use a more exact molar mass, but it's going to be pretty close to 32. So solve for mass. We would have P V equals little m. The correct R, this is atmosphere, so we've got this one. You're not going to be able to see this, 273. All over 32. Okay? So we would just solve for the little m there. So I'll do that real quick. If I make a mistake, yell at me.
Shaw, is the N in the V in the equation? Where's the decimal at?
In the which one?
250.
Oh.
Should the decimal be before or after?
Right there.
In the problem, it's after.
Yes. The reason I moved it 3 places because we have to get it in liters. Does that make sense?
Oh, okay. Yeah, sorry.
Okay, that's all right. It's all good. So, and my dots really suck on this thing, so it's hard to see that. Okay. So, like I said, that's one of the crappy things about this is that those guys are always going to slide in some milliliters or something like that, and it's going to cause you to get an answer that's close, but not exactly perfect. So let's see here. Let's see if this is right. I can't even see. So somewhere around 0.554 grams.
Hey, Shaw.
Yeah.
Why'd you use 273 and not 298?
Because I'm a dummy. It should be 298, which means my answer is going to be wrong. I'm glad I'm recording this so everybody can see how stupid I am. Who was that? Was that you, Jersey?
Yeah.
Awesome. Thanks for saving me there. All right, let's do this again. You are exactly correct. I am silly. Okay, that seems a little bit better. So typically I would say, all right, either don't use molar mass for your sig figs or use a more exact molar mass. Honestly, I don't care what you do. you guys are going to have to learn to do what your professor wants you to do down the road. Okay, so like if your professor wants you to use more exact molar masses, do that. If they're cool with it, or they give you a little bit of leeway there, that's cool as well. I'm going to say, does this look like a better answer? 0.507 dot 507. Somebody unmute and tell me if you agree with me, please. Or do you not agree with that? Morgan, what'd you get?
I was just watching you.
Oh, Morgan. I was just watching you. I think it's right. Okay. I'm going to roll with it. Nobody has a calculator right now, correct? That's what's happening here. Nobody has a calculator. So this is an example of using mass. I'm going to skip this next one because we don't. By the way, the only weird thing about this one is that it would be in kilograms, which means you'd have to deal with that. All right. But I want to do one with density so you guys can see that. Okay. Oh my God. Find the pressure in ATM for a gas with a molar mass of look at that. Got more fancy there. 77.95 grams per mole, a density of 6.27 grams per liter, and a temperature of 66 degrees Celsius. Okay. So the dead giveaway here is this word right here is density. So density is equal to the pressure in ATM, which we're trying to solve for there. And actually, I'm going to write this density down because I can directly use that. If it's in grams per liter, it is usable. Okay? Pressure times the molar mass. R, got to use the correct R. They want it in atmosphere, so we got to use this dumb one. And then see if I can not screw this up. 66 plus 273 is going to be 339 kelvins. Okay? Sometimes people struggle with solving for things that are set up like this. Like, for example, solving for temperature. People screw it up all the time. If you have issues with that, just put that over 1 and do a little cross multiply and divide. Okay? So I'm pretty sure you guys will be okay. Those of you that are here. All right. So my pressure I got was 2.24 ATM. All right. So a couple of examples. What I'm going to do today is I'm going to give you guys, I don't know how many problems I gave you the other day, 5 or 6 or something like that. Couldn't have been more than 8. I'm going to give you some that have mass and this one, and maybe also the original. So you're going to have to figure out which of the 3 variations of the equation you're going to use. All right. That's going to be our goal for today's assignment. Like I said, all this stuff is due next Tuesday. I'm just trying to condense things and give you guys time to get it done and not have to worry about it. All right. So I'm going to push stop here real quick. I'm going to stop recording maybe.